Welcome to the Explainer. Today, we're stepping straight into the roaring furnace of a marine boiler. We're going to look at exactly how heavy engineering tames extreme danger to actually do useful work. Because think about it. Inside these massive pressure vessels, water and superheated steam are held at pressures so extreme that a tiny leak doesn't just hiss, it literally becomes a high-velocity jet capable of slicing straight through solid steel. No exaggeration. That is exactly why the engineers who operate these machines treat them with absolute, unflinching reverence. If you get this system wrong, the consequences aren't just theoretical. Section 1. The Sacred Pressure Vessel. So, to really understand the stakes here, we first need to establish exactly what this massive machine is doing down in the belly of a ship. At its core, a boiler is a heavy-duty pressure vessel that uses the intense heat of combustion to convert water into steam. On steam-powered ships, this provides the raw muscle for the main propulsion turbines we talked about in previous chapters. But what's really fascinating is that even on a modern diesel-only ship, a boiler is still absolutely necessary. It provides a steady, reliable supply of essential low-grade heat. We're talking about warming up thick fuel oils so they can actually flow, heating liquid cargoes, and keeping the crew accommodations livable, especially when the main engines are stopped in port. Section 2. Water tube versus fire tube boilers. What really stood out to me here is that there are two completely opposite philosophies for building a boiler. When you put water tube and fire tube boilers side by side, it's honestly amazing to see how perfectly inverted their internal geometries are. They sound similar, sure, but they operate as total opposites to solve completely different engineering problems. Let's break it down in plain language. A water tube boiler is kind of like blowing a hairdryer around a tightly packed bundle of water-filled straws. The water circulates inside the cubes, while that searing combustion heat surrounds them on the outside. Now, a fire tube boiler is the exact reverse. Imagine running hot exhaust pipes directly through a bathtub filled with water. The heat is trapped inside the tubes, and a huge volume of water surrounds them. And because of this fundamental design difference, those massive water tube boilers are your go-to when you need to handle incredibly high pressures and rapid steam generation. They are perfect for main propulsion. On the flip side, the compact fire tube boilers, often called package boilers, well, they just sit quietly in the corner of the engine room. They're simpler, incredibly robust, and designed to handle the lower pressure daily auxiliary heating tasks of the ship without making a fuss. Section 3. Squeezing out the heat. Let's look at how this builds into an incredibly efficient energy system. See, once the boiler drum creates steam, that steam is still wet, meaning it's just barely at the boiling point. This is where the superheater comes in. It acts exactly like a hairdryer's second, hotter heating element. It takes that wet, just boiled steam and passes it through additional tube banks situated right in the hottest part of the furnace's gas path. This dries the steam out completely and raises its temperature well above boiling. And why does this matter? Well, if wet steam hits the cold, fast-spinning blades of a turbine, it will instantly condense into water droplets and literally destroy those blades from the inside. And then, to recover the heat that would otherwise just vanish up the funnel into the sky, we use an economizer. The economizer sits high up in the cooler exhaust gas path. It acts as a preheater, warming up the incoming cold feed water before it even enters the boiler drum. By squeezing every last drop of thermal energy out of the exhaust, the whole system becomes vastly more efficient. Section 4. The Sacred Boiler Mountings. Because a boiler is effectively a contained bomb, the safety mountings on its front panel are treated as absolutely sacred. I mean it. Every single mounting on the front of that boiler, the heavy glass tubes, the mechanical floats, the massive spring-loaded valves, they exist for one reason only: to prevent, detect, or respond to catastrophic failure. You can never trust just one automated system, right? Because machines can lie. You always need mechanical backups and direct visual confirmation. So, here is how the automated safety flow works in practice. First, we visually detect the exact water level in the drum using heavy-duty gauge glasses. Second, automatic feed water regulators continuously control the incoming flow, nudging it up or down to hold the water within a very narrow, very safe band. And finally, if the pressure ever spikes dangerously high, the spring-loaded safety valves will automatically lift, safely venting that excess steam straight into the atmosphere before the massive vessel can rupture. Section 5. The Low Water Threat. All of these intricate safeguards are fighting one constant, terrifying threat. Boiler water level must never be allowed to fall low enough to uncover the tubes.
The crucial point here is the golden rule of marine engineering. An uncovered, still-firing tube will overheat and fail within minutes, not hours. Without water inside to absorb the ferocious heat of the furnace, those steel tubes will rapidly glow red-hot, weaken, and blow out.
Let's test your intuition with a terrifying scenario from the source material. Imagine the alarms are screaming. Your boiler has suffered a low-water casualty. You suspect the tubes have already run dry and are dangerously overheating in the furnace. Is your very first move to hit the pumps and flood the boiler with cold water to cool it down and save it?
The textbook answer actually completely surprised me. Absolutely not. You think water puts out fire, right? But introducing cold feed water to weakened, superheated steel tubes causes massive thermal shock. The metal will instantly contract, stress, and violently rupture, turning a bad situation into a lethal explosion.
Instead, you must strictly follow emergency procedures. You secure the firing first. You cut the fuel, extinguish the burner, and stop the heat source immediately. Only once the furnace is secured and the system actually begins to cool can you even think about assessing the damage. So, looking back at all this, it's clear a boiler isn't just a giant kettle boiling water. It is a meticulously engineered system of thermodynamics. From the way water tube and fire tube designs solve different problems, to the superheaters squeezing out maximum efficiency, right down to those sacred safeguards designed to prevent a deadly low-water casualty. It is built to harness terrifying power and do it safely. But the life of that high-pressure steam doesn't just end once it has spun the turbine. It can't just be vented away. It has to be meticulously captured, cooled back into a liquid, cleaned of impurities, and sent right back into the boiler to start the cycle all over again. That closed loop is the feed system. But how do you perfectly recycle that superheated steam without the naturally occurring oxygen inside it corroding the entire ship from the inside out? Well, that is exactly what we will uncover in our next explainer.